Okay, if I don't want that brand new equation that we want to write for non-standard delta G. Wasn't part of your test, but this is where we're moving from. So what we've learned is that delta G non-standard is equal to delta G A standard, okay, plus what? RT natural log of Q. Okay, a couple of things here, okay? Number one, we have to recognize that this has a little not symbol, which tells me that this is only measured from standard conditions. 1 molar concentrations, or if we're dealing with partial pressures, it's 1 atmosphere, okay? Something else to think about is that these reactions are in 1 atmosphere of pressure and the temperature is 298. But the big key here is that when we are dealing with delta G of 0 here, we're dealing with 1 molar concentrations of my reactants all the way through, at least the start of the reaction. Or for partial pressures, it's 1.0 ATMs. That's important. Also have to realize we're dealing with a reaction quotient. For the millionth time, it's products over reactants, coefficients become exponents, and solids and liquids do not apply. Solids and liquids do not apply in a reaction quotient because we cannot measure an entropy change or a dilution. Remember, this formula was the result of a derivation from experimental evidence that particles that are concentrated, like a 1 molar solution, a solution of, let's say, ions, now goes to a 0.5 molar solution. We can gauge non-standard entropy changes by the changes of reactants and products concentrations. But you only have a concentration if you're aqueous. Molarity is moles of one thing dissolved in a liter of the solvent total solution. Okay, and we also have what? Parentheses for gases. Gases can be considered a solution. So you can have a molarity of a gas. You can have a mole of a gas existing in some what? Volume of a container. So you can have a molarity for a gas. But if you're going to consider a gas a partial pressure in a mixture, we'll use that. Okay? So what Q does for us is measure, okay, what's happening at some point in a reaction, okay, and it could be any kind of snapshot, but it's telling us what the reaction's concentrations have changed to. And that will lead us down to a non-standard. Now, why non-standard? Because we're not going to be at 1 molar concentrations. We're not going to be at 1 atmosphere. These reactions are going to be different as the reaction proceeds. Or you're not starting with these. Remember the limitation. As great as delta G of 0 is, and we know how we know what that represents. Okay, the total what? It really represents a total entropy change of the universe. Tells us about the free energy released or absorbed if something's spontaneous or not. So that's beautiful, but it only becomes almost worthless because we're never at these conditions. And not worthless, we still have a what? This is a baseline. Knowing the delta G from our tablature, we're going to change from that position some amount based upon how the concentrations of our reactants change. That's important you get that, okay? So we're going to either add to it or we're going to what? Subtract to it, okay? And that's Le Chatelier's principle, okay? And that's what tonight is about. Now I want to do a derivation to talk about something. Now, we have learned in this U diagram that reactions always work to their death, which is the equilibrium. Equilibrium is when there's no more work being done. Now, equilibrium is when you have a reversible reaction. Reversible reactions are usually when delta G is positive a little bit or negative a little bit. What does that mean? That means that you don't really go really spontaneously well in one direction or another. So if you have delta G's that are like your test, that were positive a little bit or negative a little bit, hey, that's a reversible system. If delta G is negative 300 kilojoules per mole, not reversible. That's like combustion. We call that a what? Completion reaction. Okay? So, in a reversible reaction where the delta G is 0 is positive 10 or 11, okay, or minus 11 or minus 8. Okay, these are reversible, which means that the forward and reverse have a pathway. Now, what is equilibrium? Equilibrium is when the rate of the forward reaction equals the rate of the reverse. But it's a position where the reaction's going to stop doing work. Delta G is what here? 0. Okay? So reactions always work toward that. Remember we talked about 100% reactants and 100% products? If you got a lot more reactants than products, hey, you're farther away from equilibrium, you're more spontaneous. Hey, you have a delta G, non-standard, more negative at this position than this position. Because this position you're close to being what? 0. Okay? So we've talked about this, now we're going to put numbers there. So very important. So what is equilibrium? Equilibrium is a position that the universe allows, considering the spontaneity of the forward and the reverse. Now I put K equilibrium kind of in the middle. Equilibrium are never going to be 50% reactants and products. They're going to favor one way or the other. So in general, what equilibrium is, and I'll explain, is a position where delta G of the entire process, forward and reverse, go to 0. And what it really measures is, hey, how spontaneous is the forward? How spontaneous is the what? Reverse. And it finds that position. Equilibrium is never 50%, 50%. For instance, we're going to look at a new problem where we're going to have small equilibrium constants. Now, let me help you with equilibrium constants. Equilibrium constants is actually a Q. What's a Q? Products over reactants, coefficients become exponents, solids and liquids don't apply. But what is KEQ? KEQ has the same formula. So KEQ and Q are essentially the same, except the equilibrium constant, the position of how much reactants and products you have, is a special case of Q. So KEQ is the same formula, okay? It's a special case of Q when the reaction has gone and stopped or died. It doesn't mean that things aren't going on, but the forward equals the reverse. So listen, look at this KEQ. It's small. What does a small KEQ mean? Hey, it's the same. It's got what? A lot more what? Reactants than products. Now what makes this KEQ? Q equals K when we're what? At equilibrium. And what is equilibrium? It's a position that the universe allows by evaluating, hey, how spontaneous is the forward? How spontaneous is the reverse? If we've got an equilibrium position that favors, hey, small KEQ means what? A lot more what? Reactants. That means that the reaction barely goes forward, correct? That if it barely goes forward and the KEQ is favoring what? More reactants, not like my 50% drawn, doesn't that mean that the universe is kind of more spontaneous in the reverse than the forward? So these are battling it out. Hey, I've got the reverse and the forward, and yeah, this is a little bit spontaneous, this is more, so it pushes the KEQ to this position. It's a battle royale of who is the most spontaneous when it comes to reversible systems. And if the K is small, and we favor more reactants in this position where delta G becomes 0, it really means the universe allows what? The reverse more than the forward. Okay? And that's important. So KQ is exactly what Q is, only when we're at equilibrium. It's got the same formula. So now listen, to explain this more, I want to derive the next formula you're going to use. Okay? So watch, it's really simple. Okay? We're going to now do this reaction at equilibrium. So at equilibrium, what does delta G go to? Now it's delta G that goes to 0, not this delta G. That delta G is from tablature. So that stays there as whatever it is. Plus R. By the way, the R is the Joule gas law because this is energy, right? T is in Kelvin. And then natural log at equilibrium, doesn't Q become KQ? Okay, now let's solve for this guy. We're going to do what? If I do this, doesn't it become delta G of 0 equal negative RT ln of KEQ? And booyah, we've got a new formula. And let me explain what it means. If I've got a small equilibrium constant, who is favored? Products over reactants. Right, so if this number is less than 1 for KQ, there's a lot more reactants when this reaches the depth of the reaction. You with me? So the reaction barely goes what? Forward. So listen, if KQ is a number less than what? 1. If you've got products over reactants, and these are, of course, concentrations to an exponent, but if this number is bigger than the reactants, if you're over here, isn't this number of KQ less than 1? Yeah, if there's more denominator value that is, the denominator is larger than the numerator, your value is smaller than 1. What's the log or natural log of a number smaller than 1? What's the sign? Negative. So this becomes a negative number. Times a negative, what do you get? A positive delta G. Hey, what does that mean? If you favor an equilibrium constant, that means you barely what? You're less spontaneous. Does that make sense? If I have a large KQ, let's look at another U2 diagram. If I've got a large KQ, look where the position is now. Think about this. If I have a large KQ, that means who's bigger, products or reactants?
Product.
And therefore, KEQ is greater than 1, which means when we get to the equilibrium position, there's a heck of a lot more products than reactants, correct? And if a KEQ is greater than 1, any number greater than 1, what's the log of that? Positive. Positive plus a negative makes this value negative, which means the forward reaction must be more what? Spontaneous. That makes sense. If you've got an equilibrium position that favors more products, it must mean the forward reaction has got a negative delta G. It's more spontaneous, and the reverse is not as spontaneous. So it supports that. But what the heck is Le Chatelier's principle? Well, if I know the position when it reaches depth, and I can solve for my Q, well, how is Q and K different? Q is whatever the reaction are at a certain point. KQ is what this Q is at equilibrium. So if I've got a Q that is what? In this case, less than KQ. Stay with me for a second. What does that mean? If this Q is less, doesn't that mean I have more reactants? So if I've got more reactants, think with me. I've got more reactants that I'm allowed by nature. Nature says I should have more what? Products. So if I've got a lot more reactants than I'm supposed to have, aren't I in this direction? Q is what? Q is less than K. And it's going to keep, so we're going to be spontaneous in this direction. Hey, that's Le Chatelier's direction. That's Le Chatelier's principle. When you mess around with a stress, you're messing around with a Q. What if Q is greater than K? What if you got too many products? This number is bigger than this K. Now you're going to force it to go in reverse. So we can take reactions and manipulate them by stressing them out, by changing their Q. Have a great day. Okay, don't stress out over this test. Although there's a lot of stress in Le Chatelier's principle.